In the next 20 minutes, we will cover everything that matters about this: iterative and recursive traversal, the bugs everyone writes, the edge cases, and the use cases that make it the foundation of every linked list algorithm. Let me start with the piece that does not move. This is head. Head marks the beginning of the list. It always points to the first node, and it never moves. If head moves, we lose the list. There is no way back to the start. So we make a second pointer, cur, short for current. Cur is the worker. Cur is what walks. Watch. Cur starts at node 1. We follow node 1's next pointer. Cur is at node 2. Follow node 2's next. Cur is at node 3. Follow node 3's next, and we hit null. Done. One pointer, walking the chain, until it hits null. And now you can see why traversal is the foundation. Find a value, walk till you find it. Count nodes, walk and count. Insert in the middle, walk to the spot first. Delete, walk to find it. There is no other way in. So let us write the code that makes it happen. Iterative is the version you will write in real code. It is a single while loop with 3 things you cannot leave out. Let us build the pattern from scratch, one line at a time. Pay attention to why each line exists, not just what it does. First, we need a worker pointer. Cur starts pointing where head points, but the moment we have 2 pointers, we can move one without touching the other. That is the whole reason this line exists. Now we need a way to know when to stop. Null is the signal. As long as cur holds a real address, there is still a node to process. The moment it becomes null, we are past the end. This is the only line that changes between problems. Print the value, compare it, count it, sum it, whatever the problem asks. Everything else around it is the same template. And this is the line nobody can afford to forget. Without it, cur never moves. The loop runs forever, printing the same node until your terminal fills up. Every traversal must end with this step. Let us drop a real operation into the body and run it. Print is the simplest one. Every node we visit, print its value. Now let us actually trace through what happens. We enter the function. Line 2 runs once. Cur now points at the same node head does. The condition is checked. Cur holds a real address, so we go into the body. Body runs. The data field of the current node, 42, gets printed. Advanced step. Cur reads its own next field and overwrites itself with that address. Loop jumps back to the top. Condition checked again, still not null. Body runs on the new node. 17 prints. Advance again. Same operation, read next, overwrite cur. Third pass. Cur is still real, we enter the body one more time. The data field of node 399 gets printed. Now the advance does something different. The next field of node 3 is null, so cur becomes null too. Back to the condition. This time the check fails. The loop exits. The function returns. The work is done. Look at head. We just walked the entire list, and head has not moved a single byte. That is the whole point of using a separate worker pointer. If we had walked head directly, the list would be lost the moment this function returns. Head is the only handle we have on the entire chain. Treat it as read-only during traversal. Time complexity is big O of n, order n. That means the time grows linearly with the size of the list. N nodes means n iterations, and there is no way around it. The structure has no shortcut. To reach node 5, you must visit 1 through 4 first. Space complexity is big O of 1, order 1, also called constant. We allocate 1 extra pointer, cur, and that is it. 3 nodes, 3 million, 3 billion. The memory used by traversal itself never grows. Order n time, order 1 space, 3 meaningful lines of code. This is the version you reach for almost every time. We will see why in a minute. Now there is a second way to do this, and it will teach us something the loop cannot. Same problem. Walk the list. Print each value. But this time, no loop. The function calls itself. Recursion feels like sleight of hand the first few times you see it. So, we're going to build it slowly, and then break it open and see exactly what it costs. The signature already does work for us. Iterative print took head and made its own copy. Recursion gets a fresh cur automatically. Every call has its own. We'll see why that matters in a minute. This is the most important line in any recursive function. The base case. It's the off switch. Without it, every recursive call makes another recursive call, and you fall down forever. And here's the trap. People write, if cur arrow next equals null, return. Looks reasonable. It is wrong. Skips the last node, and on an empty list it dereferences null and crashes. Check cur itself, never what cur points to. Process this node. Whatever the problem actually wants, printing, counting, comparing, it lives on this line. And here's the recursion. We hand the rest of the list to another copy of ourselves. The function says, I did my one node, you handle the tail. Each call shrinks the work by one, and that's what guarantees we eventually hit the base case. Let's run it. Two things to watch, the call stack on the right and cur above the list. Cur always shows what the executing frame is holding right now. The frozen frames keep their values inside the stack. First call lands. A frame goes on the stack. Cur appears above node 1. That's where this frame is working. It prints, hits the recursive call, and freezes right here. Not finished, paused midline, waiting for the tail to come back. Second frame pushes. Cur slides forward to node 2. The first frame's cur didn't disappear. It got captured. Look at the stack. There it is, frozen, still holding node 1. Third frame. Cur advances to node 3. The stack now holds two frozen cur values, and you can read both of them, locked in. Fourth call. Cur now holds null. The variable is still alive. Its value just points past the end of the list. The base case fires. This frame returns immediately. Pause here. The list has 3 nodes. The stack has 4 frames. That extra frame, the null 1, is the off switch. It exists for one reason: to return. Frame 4 returns. Frame 3 resumes. And cur comes back, no longer null. It's holding node 3 again, exactly where it was before the recursive call. 3 pops. Cur slides backward. The list has forward links only, but recursion is walking us back. The stack is the only memory of where we came from. Frame 1 pops. Stack empty. Cur is gone. The function has fully returned. Output reads 42, 17, 99. Same answer the loop gave us. Now, I'm going to change exactly 2 lines, and the output will completely change with them. Recurse first. Print after. That's the only change. What do you think this prints? 99, 17, 42. The list in reverse. Stop and feel how strange that is. Our list has forward pointers only. There is no way to walk it backwards. So how is the print coming out reversed? Watch carefully. This time, every frame pushes, and not one of them prints. The work is being saved for the way back. For frames stacked, cur is past the end, holding null. Output empty. Every frame is paused on line 3, waiting for the tail to come back so it can finally print. Now, the prints fire on the way back up. Frame 3 was the deepest one waiting. Cur returns from null back to node 3, and only now, on the way out, does its print fire. 99. Frame 2 takes its turn. 17. And, finally, frame 1. 42. Stack empty. The list printed in reverse, on a forward-only structure. That's the lesson. Print before recurse. Work happens on the way down. Print after recurse. Work happens on the way back up. Same nodes. Opposite order. 2 lines of code. The call stack isn't overhead. It's a memory of the path you took, and recursion lets you walk back up that path for free. Time complexity is big O of n, order n, same as the loop. The structure has n nodes, recursion or not. You visit each one exactly once. But space is big O of n now. Order n. The loop used a single, cur, constant memory. Recursion stacks one frame per node. N nodes, n frames sitting in memory, all at once. That call stack we just watched, it's not free. It's the cost. And it's not just academic. The stack has a hard limit, usually a few megabytes, a few thousand frames deep. Hand the iterative version a million-node list, it walks through it. Hand the recursive version the same list. It tries to push a million frames before printing anything. Stack Overflow. Crash. Same algorithm, different cost. So, the rule for plain traversal, write the loop. Iterative is the safer default. Constant space, no surprises. Recursion earns its place when the call stack is doing useful work for you. Reversing without a buffer. Tree problems. Anything where the path matters as much as the destination. Iterative wins on space. They tie on time. Recursive wins when you need the stack itself. So that's how it works. Now let's talk about how it breaks. There are 3 bugs that destroy linked list code. 3. They are not subtle. They are not advanced. People with 5 years of experience still write them. If you do not know these by name and by sight, your code will break. Let us name them. Bug number 1. The author skipped the second pointer entirely. They are walking head directly. It looks shorter, looks cleaner. It is broken. First iteration. Head prints 42. Then head itself jumps forward. The pointer moves to node 2. Print 17. Head slides again, now sitting above node 3. Print 99. Then head moves one more time, and it becomes null. The pointer is gone. And now look. The function printed the list once. The nodes are still there in memory, still linked to each other. But head is gone. We have no way to reach any of them anymore. Call print again. Head is null. The loop does not run. Want to free the memory? You cannot reach it. The list is leaked. Head is the only handle on the entire chain. Lose it once, the list is dead. Bug number 2. The author got distracted. Cur is set up correctly. The body is correct. But the line that moves cur, they forgot it. Trace it. Cur is at node 1. Check passes, not null. Body runs, 42 prints. Loop jumps back to the top. Check again. Cur is still at node 1. It never moved. Still not null. Body runs again. 42 prints again. Forever. Same node, same value, until you kill the process or your terminal fills up. Every traversal must end with the advanced step. Every single time. No exceptions. Bug number 3. Look at the loop condition. The author wrote cur arrow next, not cur. They thought, stop when the next pointer is null. That sounds right. It is not. Cur at node 1. Its next is node 2, not null. Body runs. 42 prints. Cur at node 2. Its next is node 3, not null. Body runs. 17 prints. Cur at node 3. Now check its next. Node 3's next is null. The condition fails. The loop exits, without printing 99. The last node, silently skipped. Output is 42, 17. Wrong, but it does not crash. And it gets worse. Now imagine someone passes an empty list. Head is null. Cur is null. We hit the loop condition. Cur arrow next means go to the address cur holds, then read its next field. But cur holds null. We just told the program to read from address 0. Always check the pointer itself. While cur is not null, never the field that hangs off it. Now what happens when the list is empty? No nodes. Head points directly to null. A lot of code in the wild has special cases for this. If empty, return early. Extra branches, extra checks. Watch what the correct pattern does. Line 2. Cur equals head. Head is null, so cur is null. Line 3. Check the condition. Cur is null. The loop never starts. The function returns. No crash. No special case. No extra code. That is the test of a good pattern. The edge case is not handled by extra logic. It just falls out of the rules. 3 rules. Memorize them. 1. Never modify head during traversal. Head is the only handle you have on the chain. 2. Always advance cur in the loop body. Forget once, and your code never returns. 3. Check the pointer itself, never its next. Otherwise, an empty list crashes you instantly. Every linked list bug you will ever debug traces back to one of these 3 lines. You know how it works. You know how it breaks. One thing left. What is all this actually for? You can walk a list. You know how it breaks. So now, what does this actually let you do? Let us run through the operations you can build on top of the walk. Print every value. We just did this one. Count the nodes. Walk and increment a counter. Find a value. Walk. Compare each node. Return when you hit it. Sum the data. Walk and add as you go. Search for the maximum. Walk and track the largest scene. Insert at a position. Walk to the spot first, then splice. Delete a node. Walk to find it, then unlink. Reverse the list. Walk and flip each pointer as you go. Notice anything? Every answer started with the same word. The walk you just learned is not one of the things you will do with a linked list. It is the first half of every other thing. Before you click away, try 2 of these yourself. They are both pure traversal, same skeleton, just a different body. First, write a function called length that returns how many nodes are in the list. Second, write find. It takes a target value and returns true if it is anywhere in the list. When you have got them, drop your solutions in the comments. I will read every one. We can compare approaches. One last thing before we wrap. Some of you are writing C, some C++. The walk is identical, but I want to show you that. Because data structures are about technique, not syntax. Same function, both sides. Look at the shape, declaration, copy, while body, advance. Identical. Difference 1. C needs the struct keyword every time you reference node. C++ does not. The type name stands alone. Difference 2. C uses null, a macro that is just 0. C++ uses null ptr, a real type-safe null pointer. Same meaning, better safety. Difference 3. C uses printf with a format string. C++ uses stdcout with the stream operator. Different mechanisms, same result. 3 differences. 0 of them touch the algorithm. The walk is the walk in any language. That is what data structures actually are. Technique, not syntax. Remember this? When the lecture started, you had to take it on faith. Now you have seen it. Print, count, find, sum, reverse. All of them, every single one, started with the same walk. Master the walk. The rest follows. Lecture 8 is where we start using this. We will take the same skeleton and plug in different bodies. Count, find, search, sum. Same walk, different work. If this clicked for you, like, subscribe, share with someone who needs it. I am Tree Junt. This was Visual Lab. See you in Lecture 8.